Hey guys, welcome to the next video. So in the previous video, we covered how we use H2SO4, right, or these other acids like H2SO4, H3PO4, which I just mentioned, to turn alcohols into good leaving groups, right? And so just to summarize what happened in the last two videos, when we use an acid like HCl, HBr, or HI, we get either the SN2 or SN1 reactions, so just substitution. When using H2SO4, we'll get E2 or E1, so the elimination reactions, right? Now we're going to go through examples of how we can turn alcohols into good leaving groups without using an acid, all right? So there's this video is going to be covering essentially these structures that you guys have seen called tosylates and mesylates, okay? And so there's the bare bone structure of these groups essentially just looks like this. You have chlorine bound to a sulfur with two oxygens and some R group. Okay, now the R group is going to tell you if it's a tosylate or a mesylate. Okay, and so what do these groups look like? So let's draw it again. So Cl, sulfur. So a mesylate, right, is going to be a methyl CH3, and these structures should at least be on your index card. Okay, please. And a tosylate is going to look like this. So it's got this benzene with a methyl on it. But you can see the R group essentially is the cutoff is right there. The bare bone structure, there's essentially a common structure between them. Okay? And so that's so those are tosylates and mesylates. All right. Now there is an abbreviated form of writing this. The mesylate, so mesylate is going to be MsCl. Tosylate is TsCl. Now there is one more that you guys can encounter, so I actually just will show you that, and that's called a triflate. So again, the structure is similar, but instead of a methyl or this benzene with another methyl off of it, you have a carbon bound to 3 fluorines. All right, and so this is a triflate. So we write TFCl. Okay, and so you should definitely know these abbreviations because they could either write the abbreviation on your test, or they can write the full structure. So if you can't remember the full structure, please put it in your index card so that if they give it to you, you'll still know what it is. All right. So what is the point of this, right? What are we going to use these tosylates and mesylates for? Okay. Well, there are ways that we can turn alcohols into good leaving groups. Okay. And so what exactly is this going to help us do? Well, remember the whole point of using an acid on an alcohol, we can turn them into good leaving groups, and then we can then use them in other reactions, right? In substitution and elimination. So this is going to be for the same purpose. We can turn them into good leaving groups. All right. And so let me show you guys how this works. Let me erase this. So we have this alcohol right over here. Okay. So let's draw this right here. Now I wrote R because I'm saying this could be for the tosylate, mesylate, or a triflate. Right? I'm not being specific right now. The mechanism is still the same. What happens is the oxygen attacks the sulfur, right? And what's going to happen is the O minus comes that carbonyl comes up. So we get this weird looking structure like this. O as a plus charge. Then that O minus that we just brought up comes down, kicks the chlorine out. So we're going to get this again now. This still has a positive charge. Okay. And so what happens next is a base. So most of the time you will see something like this. This is called pyridine. Essentially a benzene with a nitrogen at one of the carbons. Is going to grab that H, giving us this structure. Okay. So we get this structure. Now, what exactly, so what's the point of all this, right? Well, now that little oxygen with those, that bound to the sulfur with two other oxygens and the R group is a very good leaving group. Okay. So this is a really, really good leaving group because let's say we have something like Cn minus, good nucleophile. Come in, kick this out, and we're going to get this O minus bound to a sulfur and whatever the R group is. Now that O minus can resonate like this, or it could resonate like this, right? So we have resonance stabilization. So that's a good leaving group. We want our leaving groups to be stable once they've left. Now, whether we use a tosylate, mesylate, or triflate can help make it even more stable. So if I change the R group now to, let's say, the tosylate, right? That benzene with that carbon is actually helps make our structure more stable, right? It can pull electron density slightly towards it. And if I drew a triflate, remember from Ario, fluorines are super electronegative, and they can stabilize negative charge through induction. So they can pull it even better. So we can rank mesylates, tosylates, and triflates in terms of leaving group ability, like this. So the triflates are the best, tosylates are the second best, and mesylates are the worst of the three, but mesylates are actually still very good leaving groups, okay? So don't think that they're bad, it's just out of the three, it's the weakest, okay? And so let's go through some examples. So here, let's say we have this structure right over here. And so the way you could see this on the test is they can either give you the full structure or they can give you the abbreviation. So I'll give you the abbreviation over pyridine. Okay, so TSCl over pyridine. And so what exactly is this going to essentially help us do? So we, again, know we're going to turn it into a good leaving group. Now, the little thing I did here is that we now have stereochemistry, okay? So the very important concept here of tosylates, mesylates, or triflates, right, is that we can keep the stereochemistry, all right? So what happens is this is going to now keep the wedge, but we now write OTS. If it was a mesylate, would get OMS. Triflate would look like OTF. All right, the O is the oxygen that was our original alcohol. Okay, and so that would be how we would get this. So let's just again rewrite this. So we keep it wedged. That was really bad. So we keep this wedge and we get OTS. OTS is a super good leaving group. Okay? So we now have this really good leaving group, and now we can react it with a nucleophile or a base. Okay? So we can react it with something like CN minus. Now, at this point, you may be thinking, well, how does the little stuff that we did up here affect this stuff, right? Now, the rules of using OTS, OMS, or OTF as leaving groups is they follow the same exact patterns as if we had, like, let's say, a halogen, like this. All right, so this is going back to our old SN1, SN2, E1, E2 thought process, right? Not this thought process. That's exclusively using one of the acids. Now, so like if we have a secondary leaving group reacting with CN minus, right, or something that's a good nucleophile but a weak base, we'd go SN2. If it was a strong base, we would go E2. Okay, so in this case, we're gonna again do something like in this case we'd actually just go SN2, which would result in an inversion. All right, so the big concept to keep in mind is changing an alcohol to one of these tosylates, mesylates, or triflates, right? That's going to keep the stereochemistry. All right, you can see that we never, if you looked at the mechanism before, we never actually essentially we never affected our alcohol. Nothing ever attacked the carbon of our alcohol. Okay, so that's definitely something to always keep in mind. Now, is there any other way we can turn alcohols into good leaving groups? Now, what we can do is we can do essentially, we have a few other reagents that we can use, okay? And what I just showed you retained stereochemistry. These next two, or next three actually, do not, okay? So let's say I give you something like this. All right, now there's a couple that we can have here. SOCl2 pyridine. Or we could do PBr3 pyridine. Or we could have done PH3 PBr2, which is just the same thing as the PBr3. Okay, it does the same thing as the PBr3, but the concept is essentially the same. Okay, so what exactly now are we going to be doing, right? How is this different than what we've already just seen? The previous examples showed a retention of stereochemistry. The key difference here is that we will now cause an inversion. So I'll just show you the mechanism really quickly. So do it primarily with SOCl2. So we have this right here. Okay, and it's going to be reacting with this. So that's what SOCl2 looks like. So the oxygen is going to attack sulfur to kick that double bond up. And now we get this and we have the H still here, giving this a plus charge. And so now again, our pyridine, that remember we're still using that pyridine, that base, grabs the H, and we get this. All right, now again that O minus comes down, kick that chlorine out. So we're going to get bound to, let me move this over. it's going to be bound to sulfur. Oh, look at this chlorine. Okay, so now remember that chlorine that we just kicked out is that Cl minus. It's now going to come in and it's going to attack the carbon right here, the oxygen. Now it does this in a backside attack or an SN2 attack. Okay, that's the key thing to keep in mind. So it attacks that carbon, then this bond breaks over here, kicks this chlorine out, which means we get something that looks like this. Chlorine, and this is SN2. Chlorine, right? Now we have that oxygen, sulfur, right? And then like this other Cl minus that we just kicked out. But the key thing to know here is that we used an SN2. So if I erase this again, now we're going to get something that looks like this. So we just put a good leaving group on there, but with inversion. Okay, and so now we can again do substitution elimination reaction using our old rules. But the key thing here is we used inversion. And PBr3, PH3, PBr2 do the same thing, but they just add bromine. Now, because these three reagents used an SN2 mechanism, right? SN2, remember, works on methyls, primary, and secondary leaving groups. This only can work on those three. We cannot use a tertiary alcohol to do this, okay? So if they gave you a tertiary alcohol with SOCl2, it does not work. You cannot use it, okay? So please keep that in mind, all right? We absolutely cannot use we cannot use SOCl2, PBr3 on, and the other one on a tertiary leaving group. Now I do just want to make one small correction. I showed you guys that tosylate or mesylate mechanism, right? Get something like this, right? And at one point, you guys can go back to the video to see. I essentially had the mechanism looking like this. Right? With the R group and that plus charge, right? So what really should have happened is what I drew is the O minus came down to kick the chlorine out, and then we deprotonated the H. It should have really been the other way around. No, not the other way around. What really happened is we had this pyridine should have grabbed the H first. Right? Giving us something that looks like this. And then the O minus came down to kick the chlorine out, giving us all right, that's just one quick correction I just wanted to make. So in the next video, I'm going to just summarize all the things we've done with alcohols so far in terms of turning them into good leaving groups, just to make it like a neat little easy way for you guys to maybe put it on your index card or remember these things. All right, so I'll see you guys in the next video.